As the Catsby Group, our main mission has always been to develop energy and time-efficient solutions to everyday problems, and today we come to you with a solution which does just that. Our project is called Gimme Fast, which is a secure, reliable, and efficient data transmission system, which can be used in many applications. The main methodology behind our solution is that visible light is used to communicate and transfer data. Imagine a world where light becomes data. This is exactly what makes our solution so simple yet so powerful. We know that when an electrical signal is applied to a light source, such as a LED, illumination occurs. And when the electrical signal changes, this illumination can also be modulated according to the incoming data, and this can happen at very high speeds. Now, if this is picked up by a receiver, such as a photodetector, it can be converted to electrical data. Visible light communication also has benefits such as operating at very high speeds, not requiring any license, being harm-free to humans, and being safe of interception in indoor applications, which make it a good choice to choose as a way to carry data in a large range. There are four main objectives for our solution. First one is that data transportation between two terminals located 1.5 meters apart should occur in more than 5 cycles and under 2 minutes. Second is that we should have full successful transfer of data when the distance between the vehicle and the terminal is greater than 5 centimeters and data less than 10 kilobytes is transferred per cycle. The third objective is that we must have an error correction code at the end terminal to detect and correct any errors in the transferred data. And finally, the fourth and final objective is that the whole system should be constructed in under $200. Our proposed solution has 3 subsystems: image processing and transmission, VLC, visible light communication, and physical transportation. The overall system starts off by taking an image from a camera. The image processing and transmission subsystem here converts and prepares the image to be transferred to digital data. The VLC subsystem then sends the data through an LED and picks it up on the vehicle with a photodiode. The physical transportation subsystem then transports the data on the vehicle to the other side. The same systems operate at the end terminal to transfer the data onto a screen. This is an example of one cycle of the system. Now let's go into the subsystems. Our proposed solution has 3 subsystems. We will first start off with the first subsystem, which is the image processing and transmission subsystem. The image processing and transmission subsystem starts with the resizing of a photo. The Raspberry Pi camera takes a photo. The photo is then resized with Python for fast and easy transmission, and also to meet the requirements stated previously. The image is converted first to hexadecimals, and then to binary bits to prepare it for the VLC subsystem. Additional check bits are added to information bits in order to correct the erroneous bits at the receiver. Now we are ready to start the light communication. To transmit the data from the transmitter terminal to the receiver terminal, we use 2 LEDs, one for the data transmission and the other for clock signal for synchronizing both terminals. Putting 2 LEDs on one side causes disruption for both data and clock signals. So, by using the LEDs in different terminals, we achieved no disruption in signals caused by adjacent LEDs. This highly reduced the error rate of transmission. As the clock LED moves one cycle, the data LED sends 1 bit of data, and synchronized transmission occurs. The receiver puts the image data together to correct and fix errors. Errors may occur while the bits are transmitted by the light due to environmental noise or physical obstacles. The images converted from the corrupted binary bits without error correction can be seen here, and the results are not bright. Literally not bright. The key point of the error correction is the mechanism can detect and correct if only 1 bit is erroneous out of 4 bits. The burst errors is the main problem. To prevent the burst errors, the information bits are written column by column instead of line by line. So even if there is a burst error, it will not be totally in the same information packet, but will be distributed to several packets. The number of erroneous bits stay the same, but since they are distributed, it becomes easier to detect and correct them. As the last step, the corrected binary bits are converted first to hexadecimal and then to the image to be displayed. Our second subsystem is the VLC subsystem. The design objectives are determined by the requirements of the project. The time limit and the size of the total data size shape the design of the VLC subsystem. The time allocated to VLC directly affected the data rate, and the data rate is derived from the expected performance of the transportation subsystem. Before taking a look at each subunit, let's summarize the overall VLC subsystem. The VLC subsystem consists of three main blocks, which are the transmitter, receiver, and demodulation subunits. The transmitter receives modulated signal and converts the signal to a modulated light intensity. The receiver captures the modulated light intensity and converts it to a modulated electrical signal. Demodulation subunit then demodulates the modulated signal to data bits. After a series of tests, it is proven that the performance of the LED is more than satisfactory for the derived data rate requirements. So we followed a very simple design in the transmitter subunit, as you can see in the circuit animation. The components that set the upper limit to the data rate is the phototransistor. Because of that, the receiver subunit requires a more complex design than the transmitter subunit. Thus, we implemented an active load structure to get the rise and fall times that satisfied the derived data rates. Like any VLC, noise component of the communication medium has to be considered. Noise increases the bit rate error rates. Therefore, OOK, on-off keying, is implemented as the modulation technique to increase SNR and decrease the bit error rates. OOK modulation is done by microcontrollers. Demodulation was achieved with a PLLIC CD4046, which can map an oscillation input signal to a DC voltage level according to the oscillation frequency of the signal. Using OOK has its own trade-offs. OOK, while increasing SNR, also decreases the data rate. We provided a dynamic solution to the VLC subsystem concerning this trade-off. When the environment has high noise levels, the client can turn on OOK modulation, and when the environment is not noisy, the client can turn off OOK modulation to achieve higher data rates. Our third and final subsystem is the physical transportation subsystem. The physical transportation subsystem is used to transport the data taken with the help of the VLC subunit from one terminal to the other. The skeleton of the physical transportation system can be seen here. The slider platform is put onto the stillages colored in pink. The motor gear is connected to the rack. With this integration, movement can be obtained. The subcomponents corresponding to the physical transportation subsystem are shown here. An example demonstration of our physical transportation subsystem can be seen here. As it can be seen from the video, the platform moves at a pretty good pace. However, this pace can be adjusted with the code which will be embedded onto the platform. In the first three subsystems, we have achieved our first three objectives. However, our fourth objective, which is that the cost has to be less than $200, is also achieved, and the cost breakdown can be seen here. As it can be seen from the table, the parts that cost the most were the Raspberry Pi 3 model B+, and the Raspberry Pi camera, and also the WaveShare 3.2-inch display. However, our total cost, which was a total of $184.09, was still less than our $200 budget. So, we can say that we have also met our fourth objective. So we hope you enjoy watching our proposed solution. Thank you.